I'm very happy to be here. It's my first time here in St. Petersburg, and due to the initiative of Elena and Stanislav Smirnov, I have the opportunity to give a small lecture here on what I'm working on in the moment, or in fact in the last years. These are so-called term structure problems. I'm aware that you had a very good introduction to mathematical finance from Jana Belopolskaya. Still, I try to give in the lectures which are coming, and also today, a tiny little bit of introductory comments, such that you are not overwhelmed and can appreciate afterwards the mathematical theorems which are coming. If you feel that at some point there is a moment to interrupt me, please do so. After the finishing of the lecture, it is not possible to interrupt me anymore, so you should interrupt me during the lecture. Good, term structure problems. The first introductory part should tell you what is a term structure problem. And the second part, which is related to that slide, is then about a very concrete term structure problem, explaining you by means of that particular problem what the theory can do and what the problematic aspect still is. And number three is what is related to the title of this talk. These are term structure problems of volatility surfaces, these CNKK models. So this is a very concrete SPDE, solutions of that SPDE, and relationships to this volatility structure or volatility surface problems. So, but first, term structure problem. What is it? Imagine the following contract. You will recognize the contract very soon. So I take the following situation. You're asked to pay a certain amount of money. I don't give a sign for it. I will introduce a notation later. Today, this is the premium, the price of the contract, and receive, I say risk-free, so there's no default risk, risk-free 1 ruble at time capital T. This is somewhere in the future, and let's say today corresponds to little t equal to 0. Yeah. So you pay a certain amount today, you receive 1 unit of the currency in which you pay in the future. This is a stylized version of a loan. And somehow you are much more accustomed to the other way around. You go to the bank, you receive a certain amount of money today, and the stylized version tells that you pay back everything at the end. In standard terminology, you would say you receive the money today and you pay the money plus the interest on the money back at the end of the period. And the period is denoted by capital T, and we will refer to it as maturity. So this is a calendar date in the future. Let's say 10 years from now. And as it is apparent when you look at such contracts, those contracts come with different maturities. You can do it for 1 year, 5 years, 10 years, 20 years. And it is your individual choice. The choice, it's the market demand which tells you how many contracts are traded of this type at any point in time. Let's make a notation here. We denote the price of such a contract by P0T. The 0 stands for today, and the capital T stands for the maturity. So this is the first and basic notation, and such a contract is called a zero coupon bond, which is default free. A zero coupon bond which is default free. Zero coupon means that the contract is structured as I described it. So you pay today. In the meanwhile, nothing happens, and at the end you get 1 ruble back. Default free means that there is no risk that you do not get the ruble back because your, let's say, entity to which you paid went bankrupt. For instance, if the entity, the institution to which you pay, let's say, is the state of Greece, there was a default risk. So you pay a certain amount, it is promised that you get 1 unit of currency back at the end, and there was a certain default risk. How is the default risk usually reflected? By the price of the contract. So if the price is very low, there's a high default risk because you do not really believe that you get your money back. If the price is high, it means that you're only charging the interest because it is a good way how to for sure get a certain interest in this period up to maturity. So this is a standard contract. What is now the term structure? Term structure refers to at least the potentially existing curve of prices you have for those contracts. So this curve is defined for all future times, and it's a curve which you can see in every major economy, let's say in the Russian economy, at any point in time. I will show you an example quickly. A second notation, important, is the so-called yield. This is nothing else than the logarithm of that price divided by the number of years you have until the contract expires. So this is the annualized compound interest rate. And the picture sometimes says more than 1,000 words. Not sometimes. As a mathematician, we would rather say a formula says more than 1,000 words. But here it is a picture. So what is that picture? You see here a curve, and you see a running time January 2009. Here we have percent, and here we have time to maturity. This is from the European Central Bank, and this is the yield curve in the euro area at every day. So at March, let's stop it at some point, March 19, 2009, we have a yield curve. One of the curves you see here is the yield curve corresponding to March 19. And this yield curve tells you if you have a loan with 2 years, let's say the blue one is the yield curve, then you have about 2% of interest rate per year. So if you want to calculate the value of the zero coupon bond, you multiply the yield by 2, this gives 4%, and you take e to the power minus 4, and this gives the price of this 4%. So e to the power minus 0.04, and this gives you the price of the zero coupon bond, which would then be approximately 96 euro cent. So this is how the technology works here and how the notation works here. And you see apparently that every day this yield curve changes. This changes a little bit. Why did they take a period 2009? Because in this period it was heavily changing, and so you see a little bit that there is a motion actually going on. So you see here the guy every day is changing a little bit. Why is it changing every day? Because every day loans are taken, and every day loans are granted, and every day banks calculate out of their estimate of the state of the economy interest rates, and these interest rates are changing every day a little bit. In the moment I would stay on a descriptive level, so I would not like to explain it. I rather see that there is the short end of the curve. So this is the interest you receive when you give a loan overnight. So you are, let's say, one of the London banks and another, or one of the Frankfurt banks in that case, and another bank asks you, do you give me 100 million euros overnight? And this is what you charge. If this curve here is kinky, this means that in the short end, if you have something which has a minimum here, in the short end, the banks do not really trust each other. This was at that period particularly the case. There was an issue of that banks said, if another bank asks me today for 100 million euros, this might be that I do not see my money back anymore. If they ask for 2 weeks, it's better. Therefore, the 2 week is a little bit lower here than the over the night situation. Well, but there are different explanations coming from the particular structure of the market at that time. Nevertheless, at this point, I just want to introduce this stochastic process to you, that you see every day you have a curve. The curve is moving somehow, and I would like to introduce to you technology, how we can understand this movement. It's very important in mathematical finance that we are sticking to data. So there's a very descriptive approach, like in statistics. It is only after you have been choosing a model that you start a little bit to think, what could the model mean in economic terms? But it is not this approach that you first say, you model the 500 banks which are involved here and all the 50,000 loan takers, and then you deduce this curve. Why do we not do that? Because it doesn't work. It is a too complex problem. It's like in statistical physics when you want to describe the behavior of this desk and you start with the Schrödinger equation directly. You end up with a problem. You have to do something. And one way how to deal with that is to take a descriptive approach and first to understand a little bit what we actually want to describe and what we want to understand. Okay. So how do we approach such a problem? What does mathematical finance suggest? As always in science, there is a normative part. Let me write it in a language you can. Normative, and there's something descriptive. So when we talk about this realization of a stochastic process which takes values in the set of curves, we are not starting with any stochastic process and say we could take anything. We still ask ourselves some normative facts, normative questions. What are those processes and what are properties those processes should have? What is one main property which we for sure can say is true in most of financial markets and which is somehow a paradigm number 0? This is something which is called no arbitrage. So in economic terms, it's a statement about markets. And in terms of mathematics, it will be a functional analytic statement about stochastic processes. What is the statement about markets? The statement about markets is when you invest into a market of interest rate products, you are not able to come up with a portfolio strategy which gives you a certain gain. Sounds very basic. I repeat it again. So when you are investing in such a market, this means you are buying, let's say, a loan 1 year, 5 year. You are selling a loan with 10 years and so on. So you build up a portfolio. And no arbitrage means it should not be possible to build a portfolio which gives you a certain gain. Why do we claim that? Because if there were many of those portfolios, a lot of people would not sit here. They would go to the market and play those portfolios. And with that, from that moment on, those portfolios would stop existing because there are counterparts taking those risks from you. And since you have no risk to lose, they have no possibility to win. And such a situation is not very natural and not very persistent in markets. So this will stop existing quickly. So there's no arbitrage property that there are no portfolios which guarantee a certain gain. This is a very clear statement, and every stochastic model should have that property, which we use. That's in fact quite a strong statement about the stochastic model. So we know of a lot of models which do not have that property. And I show you some conclusions which follow out of that. What did you have a question? No? Okay. So let me put it in very simple terms. Even though it is not a simple statement, it's called the fundamental theorem of asset pricing. And I formulate it in a mathematically not fully correct version, because the mathematically fully correct version is delicate to write down. I just write it down in sort of little bit easier terms. Let's say you have a finite time horizon market. So these are products traded on the market like our bonds. And you assume that at least one of those products is always positive. So this is risk-free. Risk-free only means that there is no risk that you buy the product and then it has value 0, because then you lost everything. Risk-free product. Then the statement that there does not exist a self-financing portfolio V such that the portfolio starts at the value 0 and has with probability 1 a non-negative value at time t, and with positive probability a positive value. This statement is equivalent. I write it now up here, but I write it, it's not fully true what I say, to the existence of a measure which is equivalent to the physical measure under which this process is modeled or given, and the process discounted by x0 is a Q martingale. So it's a funny statement. The statement is you do not have such a portfolio, which is nothing else than a linear combination of those guys, which you adaptively rebalance. Self-financing means that you do not give money in and you do not take money out. So the situation is, what is a portfolio? I give you 1,000 ruble. You decide to buy a share of the first one, a share of the second one, and so on. Then you wait from today to tomorrow. Tomorrow you have a certain value, let's say 995 rubles. You rebalance your portfolio a little bit. The day after tomorrow you have maybe 1,002 rubles and so on. This is a typical self-financing portfolio. With such a self-financing portfolio, it should not happen that you start at zero and end at something positive. And this statement is equivalent to this projective geometry statement that you divide by the first guy, which is non-zero, and you find a measure which makes those new stochastic processes martingales. Yeah, that's a statement. That's the fundamental theorem of asset pricing. It's a conclusion of a version of the Hahn-Banach theorem, and quite a delicate conclusion. So the proof, finally established, took quite a long time and is not easy. Tomorrow in my first lecture I will report a little bit on the proof, and you will see, geometrically speaking, there's a simple message behind, but it is clear that at each point there are quite important details to do. So that's the normative part. We do not take any process. We take processes which allow for an equivalent martingale measure. And usually we are not even modeling with respect to P. We are right away modeling with respect to this martingale measure. Why do we do that? Because from a point of view of measurement, of observation of a stochastic process, the most difficult to observe quantity is this difference between the martingale measure and the real world measure. And establishing a model on that level is already interesting and difficult enough. For this you can take quite ad hoc ansatz possibilities. So this is the normative part of this approach in mathematical finance. We do not take any process. We take processes such that you have one process which is non-negative. This is often called the numeraire, and you divide by that numeraire process and you end up with Q martingales. Yeah. For instance, if the numeraire is 1, you can choose it in many cases like that, then the processes are Q martingales. This means everything like a fraction, a Brownian motion, everything which is not a semi-martingale is excluded. It's not possible.
You said that this is not completely true.
Now, what is the true statement? The true statement is always that direction. This direction is the difficult direction, and what is not true. So if this is continuous time, you have to make a couple of steps. First, you have to generalize this property a little bit. You cannot write it directly like that. You have a sequence of portfolios, and you are not greater than 0, but the sequence is less and less, with the sequence converging to 0, only a little bit negative. And here you get a little bit positive on a set of probability greater than 0. So you have to make it in the language of sequences. And then it is usually not a martingale, it is a sigma martingale, which is a generalization of the notion of a local martingale. And I want to avoid to tell you what a sigma martingale is, since people who were using it in the 70s in stochastic analysis, they thought that this is for sure a notion nobody will ever look at again. Before it appeared in mathematical finance, now every second banker knows what the sigma martingale is, which is funny somehow. So one of the many examples where very intellectual concepts of mathematics entered quickly areas of applications through one important use. So this is why I say it is not completely true. But as you know, local martingale and the sigma martingale has to do with jumps, presence of jumps, absence of jumps, and uniform integrability. I leave that away here. These are details. Good. I'm at the end of the introduction of the introduction, and I write down what I'm. Yeah. Let me start a little bit now with the second part of the talk. Yeah. Term structure, theory and practice. So I go now a little bit through the slides and I comment from time to time on the slides. So, sorry. We understand now what the term structure of bond prices is. So this is the value of a stylized loan in any major economy. And usually we talk of the term structure of yields, which is quoted, and you find it on the webpage of the European Central Bank. There are different term structures which we know. Another one, term structure of commodity futures prices. When you're dealing with electricity, you sometimes want to buy certain amounts of electricity energy which is delivered today, tomorrow, in 10 days, in a year, and so on. And there is a term structure of those prices. There are term structures of option prices, and I'm going to speak about that in about 20 minutes. So I'm not commenting on that furthermore. What is the feature from a point of view of stochastic analysis? First, we are looking for stochastic processes which are taking values in curves. Since this market is potentially infinite dimensional, I said we have a curve which we obtain. So the stochastic process will take values in curves, and it is also usually quoted as a curve. You saw on the European Central Bank webpage, you find a curve. This is the yield curve. So the process should be curve valued. But it is a curve which represents the value of a stochastic process. So in terms of mathematics, you would say this is a solution of an SPDE, where the stochastic features are very particular. So you saw here, you have a changement from today to tomorrow, which is a little bit, this means 2 points on the curve are strongly correlated. There's a very strong correlation from one day to the other. It's not at all like that, the 2 points on the curve which are close, that they move independently of each other. They move not fully dependent, but only a little bit of independent movement is inside. So there are strong correlation features. As we all know from statistics, it is usually quite hard to model nonlinear, high-dimensional movements of observables which are strongly correlated or dependent. So the prices depend strongly on each other. There's a typical shift dynamics. The bond today with 20 days to maturity has 19 days to maturity tomorrow and stops existing in 20 days. Yeah?
Does this curve depends on the country?
Yes. In US it is more or less flat now. This means money is printed. In Japan it starts taking off a little bit. In the Eurozone it is also relatively flat at the beginning and then it goes up. It depends a lot on the country. No?
What about Russia?
Does it exist? I would say the Russian yield curve is quite a well-described object. It is not that it does not exist. There was a default event in 1998. So the starting had some, there were some difficulties 8 years after the change in starting, but it is nowadays, I think, quite liquidly traded, and it is there. I mean, it is not, as far as I know about the details of the Russian market, the zero coupon bonds are rarely traded. So you always have coupon bearing bonds, and you have to calculate the values of the zero coupon bonds out of that. And I know a couple of people in Moscow working on that. Well, it is, I mean, in every major economy this is done, and Russia is one of the major economies. So you have this shift dynamics, and you have a calibration problem. I mean, you probably asked yourself already, a curve is always nice. But how do we get a curve in a potentially infinite dimensional market if there are, let's say, if there's only one point given on the curve? Well, then the curve is a guess. The curve has not much to do with the market itself. In the Eurozone, we have a lot of points on the curve at the short end, a lot of points here, a lot of points here, and at the very long we have. So this estimate is quite stable. But still there is an initial problem of calibration. It might happen that, in fact, you do not have points on the curves, but you have some linear transformations of points on the curve which are actually traded. And sometimes these linear transformations are not nicely invertible. So there's an initial calibration problem which tells you you should start with a model for the curve, and then you can say how it looks like. The question is which model to take. The initial calibration problem. What do they do here? You see it at the right-hand side. Maybe not at the right-hand side. At some point it is written that the parameter file here contains so-called Svensson data. So this is a 6-parameter curve which is used in order to fit this. And every day the data come from the market, and then the Svensson curve with its 6 parameters is taken, and there is a least square optimization procedure running, and then the 6 parameters come out of it. But there is something ad hoc here inside. Why do the people do that? Because nobody came up with a better solution. It's still ongoing what to take, what is good here to use. Because it might well be that this approach with the Svensson function family is introducing a noise which might be unfavorable for your problem. Good. So these are.
How do you calibrate the model?
This is then the next step. You see, this is just what I'm talking about. It is now we are only talking about how to get the initial curve. And next we have then to take the time series of those curves and then to estimate out of the time series model characteristics. So it is quite an intertwined problem which we have here. For the initial calibration, you already need a little bit of model. Then you get a curve every day, as you see it from the European Central Bank webpage. And then you can say you take your most favorite SPDE and you try to crank out the characteristics of the SPDE from the dynamics. What do people do? Because what I was telling here sounds very fancy. So why do we need models? We need models because we want to analyze risks of decisions, compute hedging strategies, price contracts which are based on the yield curves in the future, and evaluate risks for authorities. So if you are an insurance company, you have to evaluate your current portfolio in a year, and therefore you need to have a distribution of yield curves in a year, and then you calculate what is the value of your portfolio. Usually your portfolio is yield curve sensitive, and those values you have to report to the regulator. The regulator tells you that's a good risk, or tells you you should have more capital aside in order to cover problems which might show up. So for such purposes you need a yield curve model, and for others, many other purposes. What do people usually do? Most of the people take a Markovian factor model, Some take a principal component analysis inspired model, and very few, and one of those guys you have in front of you, take full term structure models. So I'm somehow advocating for the third choice. The factor models are the first ones. They are easy to implement, but they have some severe drawbacks. One is the recalibration problem, and the second one is a statistical drawback. The covariance matrices those models produce are very low rank. With low rank, I mean 1, for instance. 0 would be too low, because then there's no stochastics anymore, but 1, as low as possible. Which, PCA models are funny, because a lot of people would say, well, PCA is what they do in statistics, and they know about all the properties of that. But there has been a nice theorem, which partly was proved by myself some years ago, that a PCA model is usually not free of arbitrage, which is funny. So when you have a PCA-driven model, it is very natural that you have an arbitrage in that structure. Why is that? The reason is that you take a nonlinear transformation of data. Yeah? Usually with PCA you easily manage to make that guy martingale. Yeah? And then you take an exponent. A PCA model means you calculate, let's say, in already very advanced way, you calculate instantaneous covariance matrices. You calculate the spectral decomposition of this covariance matrix. This gives you eigen directions, and then you say, well, my most important direction of movement of the yield curve is such a movement. So you always move in that direction, and you make an ansatz. Usually you move like an Ornstein-Uhlenbeck process in that direction. The second most important is the second eigenvalue guy, and so on. And then you do that, then you have somehow that those guys are martingales, but e to the power those guys are not martingales. And this is a severe problem if you insist on being arbitrage free. Yeah. This is PCA type analysis. And term structure models have the disadvantage that they are quite difficult to implement. These are above all SPDEs, but they are reasonably structured. So model specification through data is not ad hoc. You can somehow say what is going on. So I show you first how a factor model looks like. What do people do? So now we are back to term structures. We want to write down a martingale model for bond price divided by a numeraire. What do we take as a numeraire? In the bond market, we take the so-called money market account. This is nothing else than overnight loans invested into itself. So it's called as a rollover portfolio. So the ansatz is you say you take a stochastic process, your most favorite stochastic process, let's say an Ornstein-Uhlenbeck process. You define this money market account, and then you say, if I want to have an equivalent martingale measure for those guys, I do a little back on the envelope calculation. Let me write it down. So you want to write stochastic models such that the traded object divided by the value of the numeraire is a Q martingale. Q martingale means that this quantity conditional expectation equals that quantity. Why do I bore you with such an easy statement? Because now I say, well, I have a particular value which I can introduce here. This is capital T. Why? Because at capital T I know that the value of the bond is 1. So now I obtained a very simple formula that exponential minus from S to capital T BRU dr, sorry, conditional expectation on Fs equals to PST. So this means in that particular market, when I give you a bank account, a money market account, this formula gives you the bond price. So every model of R, of capital R, gives you a bond price. Now what do people do? Let's say the second most famous example is the Cox-Ingersoll-Ross process. So Cox, Ingersoll, and Ross were taking in the middle of the 80s this type of stochastic process. This is a very well-known stochastic process. If you go to the book of Revue Saint-Yor, you obtain a squared Bessel process here, and we know that in those processes it is quite easy to evaluate this stochastic integral with a Feynman-Katz approach, and you obtain this guy here. So in that case, you can quite easily come up with a model which provides you with bond prices driven by this short rate process. What do you see here? So the phi and psi, I made a little error here, but it is not so important. I should have divided, or should have multiplied at the left-hand side by capital T minus little t. So when you take the logarithm of the bond price, you see an affine combination including the process R and two deterministic functions phi and psi. Yeah?
The R, it's the same?
Yes. Sorry, it should be an R here. This should be an R. The B is the whole guy. So this means here, when you look at the stochastic features of that process, you see that when the y changes, so when the yield curve changes in a little increment of time, it only changes in one direction. The direction is given by the psi. So there the instantaneous covariance matrix of that stochastic process has rank 1, which is very low dimensional for an SPDE. We did not see an SPDE, but there's even an SPDE associated to that process, which maybe I show you later. So this means here we have something which we can calculate. This is why people like it a lot. As always in finance or economics, or as always in sciences, a model does not help if you can calculate nothing. You tweak the model as long as you see at least one type of formula. And since this is already a complicated problem, people started with such types of models because the dynamics of the capital R process is not completely unreasonable, and you obtain such a dynamics for the bond prices. Yeah?
What is the connection between phi and A?
There is a so-called system of Riccati equations which you have here, and those Riccati equations give you the phi and the psi. Yeah. So the psi is in fact the Möbius transform as it is usual for Riccati equations, and the phi is an integration of the solution of the psi equation with respect to some other transformation you have there. This is well studied and well known. So what is the consistency problem? The problem is now very apparent. What the market gives you is that curve. So when you take the parameters which you have here inside, this is the A, the B, the C, and the R0, then the market tells you today you should choose A, B, C, and R0 like that. Yeah. On the other hand, you would say, wait a moment, the R is not something you should fix now. The R is a stochastic process, and this stochastic process describes your money market account. So this is an observable process. If you have something observable which follows such an equation, in fact the C, the volatility of that guy, should come from a time series. And the time series should give you the value for that. And the A and B can come from some estimator which you have on the time series. So you suddenly have two competing ways of fixing the parameters of the model. And these competing ways, when you do it every day, will provide you with quite different results. And this is what is called a recalibration problem. So even if you manage today to convince yourself A, B, C, and R0 are chosen appropriately, and you explain more or less well your curve, tomorrow things will be different. You will have a different A, B, C, and the tweaking will not help anymore. Yeah. So there is a problematic aspect here because you have two observations of one and the same guy, and you are not really able to say which way is superior of estimating the parameters to the other way, because both are important. Why does the problem come, or why do we have that problem? Because we start with this process RT, and we impose right from the beginning that everything is somehow explained by this low-dimensional factor process. So there's a very ad hoc approach. There was a little way out of that, and you would say this is a typical mass finance way. The mass finance way is saying, okay, if we have a problem of calibrating, is we make that guy time dependent, and we can on the one hand make this curve, we can fit it perfectly. On the other hand, we leave that free for estimation from the time series. This looks at first sight okay from an analytic point of view, but when you look at it again, it does not solve the recalibration problem at all, and it says well known that it does not do that. This is called Hull-White extension. But it has one important feature. This explains how the problem which I introduced before is related to an SPDE. So we have here an SPDE running, which is solving a certain stochastic partial differential equation, and which is staying on a very low dimensional submanifold of your Hilbert space of curves. I don't go into that geometric statement now, but I will work on this geometric statement in my lectures. So you will see very precisely what is the this SPD interpretation. Good. So apparently the plus minus are the following. We have the models are free of arbitrage, easy to communicate, to calibrate, and to implement. But there is too much structure fixed at the beginning. Recalibration is quickly leading to inconsistencies, and Hull-White extensions do not solve these inconsistencies, only in an artificial way. I don't talk about the so-called market price of risk. This is the difference between P and Q, which we did not even talk about. What is the approach I like? This is the so-called Histrio-Morton approach. There you say we have this curve-valued process, and we write the Markov process on the yield curves. So starting process is not a factor process which you ad hoc write down, but it is a term structure of yield curves, And the His-Morton equation is an equation which expresses the absence of arbitrage. It looks like that. So you have a transport operator, some drifts, a volatility operator, and some jumps. Now you would say, well, it is quite easy to write a complicated equation. Can we do something with this type of equation? Is it possible to use it? And the answer is yes, but this is very recent technology. So every problem is solved except that it is not easy to work with that equation. Everything is separated. You can do your initial calibration. You can do estimation of the volatility structure. You can even do an estimation of the jump structure. The different estimation techniques do not interfere with each other, such as in the factor problem. But there is a lot of technology and computational technology involved, and this is making it delicate. Say it again. Very good point, thank you. Usually the stochastic differential equation is written not with respect to t, but with respect to x, and x is capital T minus little t. This is not the maturity, fixed calendar date, but the time to maturity. This is a more natural way of parameterizing the problem.
And this is Poisson measure?
This would be a Poisson measure if you believe that there are jumps in your term structure.
Delta?
Delta is the height of the jumps. It's just a general semi-martingale which you write down. Just nothing. I mean, if you look at it from a discrete point of view, you have a little bit of shift, some drift, some diffusion part, and some jump part. It's just to write it down in its generality.
And then our goal is to keep all those inputs.
Yes. So what is the best observable quantity? This is the process itself. You have a time series for that. The second best observable quantity, if you fix a time series, is the volatility. This is a pathwise observable quantity. The third best observable quantity is related to the jumps. And the not at all observable quantity is the market price of risk. This you have to filter out. This is the way how you... It depends how you... You can make them stochastic, you can make them state dependent. It's just a general structure how it looks like. What does it make free of arbitrage? Freeness of arbitrage comes from the fact that the alpha is a certain function of sigma and of delta, and the mu is a certain function of sigma and of delta. If this is the case, it is free of arbitrage. This is the theory which we have behind. So this is the theory related to term structure problems, and well, I see that it was a little bit ambitious to think that I'm able to talk about the volatility surface models. Let me say something which is now very recent first, and then a statement on how the lectures will proceed in the next days. So, the His-Morton technology. Geometric point of view. Usually we have a Hilbert space of curves. And let me draw it by an egg, which I put here. So a His-Morton model is then a stochastic process moving, let's say, in that egg somehow as a stochastic process. Why do I draw such a surface here? Because as I said before, if I have a Hischer-Morton model which is related to Coxingers or Ross, this means that the instantaneous covariance is very low rank. And this means that in fact we have a foliation here in that Hilbert space, a foliation of surfaces. The Hilbert space is foliated by surfaces, and if you start your SPDE in one surface, it stays within this surface. These surfaces have a very funny structure because they are affine. They are not curved in one direction. In the other direction they are curved. This is called ruled surfaces, and this is nothing else than what I showed you before, which was discovered 20 years ago, that you have a time-dependent phi here and a psi here. So in that direction you have something affine, and in that direction the point where the affine, where the subspace is attached, is moving around in space. So these are those two-dimensional surfaces where the process lives on. So the statement I said before is that we can relate to the Coxingers or Ross a particular Hischer-Morton equation. So some Hischer-Morton equations have this foliation structure. There's a theorem which we proved about 10 years ago in Journal of Functional Analysis. This tells if the Hischer-Morton equation allows for a foliation. So we ask ourselves, what are the guys which allow for such a foliation? Then the conclusion is, and I say it now very vaguely, that there is a Coxingers or Ross type factor process behind. So the particular situation which I showed here to you is in fact a generic situation. If you have a foliation of the Hilbert space where the process lives on, then this foliation comes from such a type of square root dynamics, which was funny and completely unexpected. Because you would say you can start with any factor process, but then you cannot associate a Hischer-Morton equation on a Hilbert space on it. You only have a process which starts here and goes a little bit in some submanifold, but you do not have on an open subset of your Hilbert space of curves a Hischer-Morton equation which is compatible with that process. So this theorem tells you, in fact, there's a very restrictive dynamics going on. Either it looks very simple, or it is spreading out in space. It does not stay in a low-dimensional submanifold. So this is a statement which is, in terms of stochastic analysis, you would say very extreme. Either you have some ergodicity of the process, or you stay in this Coxingers or Ross type of dynamics. You would say, well, that's due to that equation, and maybe one has to lift some assumptions at some point. So it seems that these are very extreme words. Either you have something which is easy to calculate and not useful, or you have something which is ergodic and therefore quite difficult to calculate, because it is usually difficult to solve an SPDE numerically where you do not stay in some finite dimensional set, because you have to calculate, in fact, the whole process, and you will never have an exhaustive way of understanding the process by observing, let's say, finitely many points on your curve. Is that all? The statement is no. This is somehow a recent progress which we try to make, and these are these so-called consistent recalibration factor models. So this is somehow not having such a finite dimensional foliation, but still having all the advantages of that. Yeah, I only take 2 minutes now. How does that work? It is somehow an idea which we had a couple of months ago, saying it's a little bit hard to express what I actually mean with it in terms of one color, therefore I put the second. Imagine that you have not only one foliation on your space, but you have several foliations on the space. Foliations which can also be point dependent. So at every point you have a way how to foliate space. And this foliation is chosen in a way that it corresponds to such a type of model. This is the factor model which is behind. Let's say a Coxingers-Ross model, but in this Coxingers-Ross model you have an A, B, C, which depends in fact not only on little r, but it depends on the capital R, on the whole, not on the capital R, but it depends on the little r, on the whole yield curve. Now you would say, yeah, nice, but this destroys the whole structure, because then you cannot calculate your conditional expectation. Everything is out. This was it. There's difficulty. Now you think about how you construct stochastic processes when you solve, let's say, a stochastic differential equation. What do? You take your stochastic process, you discretize it, so you go over a small time interval, and at this small time interval you freeze the coefficients. So you have a constant drift and a constant volar and some jumps. And then you let this little chunk of Levy process run one step, then you change your drift, your volar again, and then you let another chunk of Levy process. So a concatenation of Levy processes is the Euler scheme. And this concatenation of Levy processes gives you then the solution of your stochastic differential equation. You could think now that you have a His-Morton equation, a general His-Morton equation, but locally this His-Morton equation is produces movements which correspond to such a factor model. So this is like you move for the first instant in time in the first foliation, then you end up here, then you move in the second foliation, and so on. So you concatenate such type of simple models, but you concatenate them by their traces which they have as an SPDE, which is a funny way to think about this Markov process, a one-dimensional Markov process. You lift it to an SPDE, you solve the equation there, which you can write down, and then you make the solution dependent on the state variable, and you concatenate it. The attentive audience will say, well, this cannot be completely for free. There must be something which is a difficulty here. And the difficulty is apparent. The difficulty is you have to tell your process on which leaf it lies. First, you are started at the point, you have a foliation associated. Then you make a movement along. You have a new foliation at the next point. And this is like telling now, at this point you take another foliation. How do you do that? You have either to prescribe it or to determine it from data, and this is a delicate procedure. So, but at least, this is what one can say as a conclusion, less delicate than solving the full His-Morton equation. The message is concatenation of solutions by not Levy processes as we do it usually, but by these factor model inspired processes in these leaves of the foliation. I stop with the talk here and I do not come to volatility surfaces. Volatility surfaces would be the same type of problem but one dimension more. You do not only have a yield curve, you have a whole surface. This is related to another market, and in this other market you have those surfaces which represent certain term structures. So, but you understand, when you understand what I tell you, what I told you today, it is analytically more involved but the same complexity of problem. What is my lecture about tomorrow and the day after tomorrow and on Friday? So it will be about this type of theory, but everything is discretized. So there will be no real analytic problems. It will be developed from the scratch, a theory where you see all those term structure problems, including this foliation theory, but from a fully discrete point of view. So the SPDEs are then, in fact, difference equations. All the processes are running in discrete time. The maturities are running in discrete time. We only have sequences of random variables being very strongly correlated and satisfying a no arbitrage condition and satisfying certain properties. And then we come up with a theory to solve ergodic systems of those equations in a very easy way with this changing foliation approach, which is a little bit funny that one is able to, let's say, deal with such equations in such an easy way numerically. Okay, I stop here and I leave some time for discussion. I talked enough for today. Thank you.
Any questions? You said that there is some connection with geometry.
Now, your theory of foliations in geometry plays a certain role. So in order to prove that statement, you need to calculate Lie algebras of vector fields, the vector fields which are related to this equation. And you have a system of equations there, and you claim that this system of Lie algebraic equations has a certain dimensional constraint, and out of this dimensional constraint, you obtain the geometry of the foliations. Like, I mean, we know all that. We know that from integrable systems. Whoever had his course in symplectic geometry did such calculations. Yeah.
Are you working with default-free situation only, or you can involve?
That's a big problem in mathematical finance, that the main theorems of mathematical finance need at least one default free numeraire in the market. Otherwise, there is no real way to talk well about, or talk in an easy way about being free of arbitrage. Being free of arbitrage, I call it always, mathematically speaking, a projective statement, so you have to divide by something. It's relative to another quantity, and if you have no quantity which does not vanish, then you have a difficulty to express that. In that setting, you can talk about defaultable bonds, but you need a default-free bond market, and you can on top look at the second market, which is defaultable. Then you have two curves, they move in certain ways, and the first one is default-free and the second one can default. Defaulting means that you have the curve together with the recovery. The recovery is the amount of money you get back at the end, and this will be 1 or less than 1. This is an additional random variable which is modeled then. And you can see it like a foreign exchange market. So you can model it like an economy, let's say like Russian economy versus the US-American economy. You have the exchange rate between ruble and dollars, and you can say, from the point of view of the Russian economy, if you assume that the Russian economy is default-free, The US economy is an economy where you invest a ruble or some money today in order to receive an amount of money in the future, but you do it by investing into the US bond. So you have to exchange today ruble to dollars. You buy with the dollars a 10-year dollar bond, and then you receive in 10 years $1. But this dollar in 10 years might be less than what you paid today. And from that point of view, it looks like default. You can model it like that. A default event meaning not necessarily that you go to zero, but that you receive less than you have invested. So therefore, the answer is defaultable structures can be easily considered here, but you always need one structure which is default-free. Okay.
Other term structures existed in insurance?
I mean, the most important term structure in insurance mathematics is the interest rate term structure. Because when you ask actuarial mathematicians or actuaries what are the two important risks in insurance, it is the interest rate risk and the risk of a damage. Yeah. So when applies for that, this is overall the whole economy. When a life insurer receives a premium in order to insure individuals, then there are two risks to be considered. One risk is the group of individuals and what is their mortality. This is the first risk. And the second risk is which interest rate is promised on the money. And the interest rate promised has to be gained by investing carefully the premia into bonds. And since you receive the premia into the future, you should know which bonds to buy, and this depends on the model. This is not completely model-free. Yeah. So therefore, there's a huge risk, interest rate risk there. Yeah. It's a very natural risk. It is everywhere. Every pension fund, every pension scheme has an interest rate aspect. Thank you.